pessoa, um cientista interdisciplinar. O John fez o doutorado dele em Harvard em
But I'm Canadian. Very important.
John Bush. Ele não é parente do George Bush.
It's an important distinction to make.
Fez o doutorado dele em Harvard em geofísica.
Yeah.
Geophysics. Right?
That's right. That's right. Yeah.
Depois foi para Cambridge, no departamento de matemática aplicada e física teórica, que é o famoso nome fez um pós-doc lá, e depois foi para o MIT como professor assistente e lá ficou até hoje, é professor titular do departamento de matemática do MIT. E o John, como eu falei, um cientista com perfil interdisciplinar muito forte, é doutorado em geofísica, é professor do departamento de matemática do MIT e é um dos poucos, não é o único, tem poucos portugueses, também se eu falar coisa errada que ele me corrige. Ele é um dos poucos no mundo, não o único, mas é um dos poucos no mundo que está no departamento de matemática e tem um laboratório de fluidos, não que nem o do INPA. O laboratório de fluidos do INPA, os fluidos são virtuais. Os fluidos do John é um laboratório de fluidos, é fluido para valer. E o John se alimenta muito intelectualmente, né, do laboratório de fluidos, quer dizer, e esse curso dele é um curso que tem dentro aqui do INPA uma perspectiva física muito forte e que vai tentar mostrar onde entra um modelo matemático, ideias de muitos problemas ligados à instabilidade e principalmente a área que o John assim, muito próximo ao coração dele e muito forte aos problemas de fluidos que envolvem tensão superficial. Né? Então, o curso, a ideia do curso é mostrar, motivar da física, dos experimentos de laboratório dele, aonde que vem os modelos matemáticos, tudo isso. Então, né, eu falei para ele, a primeira semana também meio estranha, porque muito colado no ano novo, então vou começar devagarzinho e... John.
Very good. Okay, thank you. Thank you all for coming. I remember when I was a student, I used to hate when they had lectures on January 2nd because that meant that I had to travel on January 1st when I was never in much of a state to travel. So I appreciate your coming in. So today we will be taking it slowly. I'm going to basically give you a tour of the sorts of things that I'm interested in. I'd also like to find out what you're interested in because I can tailor my lectures accordingly. I gave a course at MIT last year on this subject, and I have more material than I need for this course, so I can choose things if you're particularly interested. But in terms of my development in this course, so these are the sort of three areas which I have worked in. So basically started here, so understanding basic problems with drops and bubbles and fluid sheets, how we understand the influence of surface tension on, say, impact dynamics, on waves. And so once one has a fundamental understanding, then you simply look for areas, rich areas of application. And I started here. For a long time I'd worked in this area, and I said there must be problems in biology which are dominated by surface tension. And so if you realize, as we'll see as we develop the course, surface tension dominates physical systems which are small relative to raindrops. Okay, so basically the world of insects is dominated by surface tension, and so I've done a lot of work on how insects exploit surface tension for propulsion, for feeding, for water repellency. So both plants and insects use surface tension, and it's critical for their survival. Okay, and so this last third thing here, that's going to, when I talk about this, we're going to turn the camera off because it's a rather hot topic and controversial. But this is something which has come up in the last few years. A friend and collaborator, Yves Couder, who Andre is also, he's been, I think, entrained, sold. But we're looking at a peculiar system, a hydrodynamic system in which drops bounce on a vibrating bath. So we basically take a fluid bath and we put it on a loudspeaker, and if you put a drop on it, then it bounces. And in a certain regime, it starts walking, and it interacts with its wave field in such ways to move. And this object now has both a It's both a particle and a wave, because it's a particle being guided by a wave, and these walking droplets behave exactly as do quantum particles when they're passed through double slits, for example, and I'll go through that today. But it's basically introducing the possibility of modeling quantum mechanics on a macroscopic scale. Okay, so it's a very interesting and important problem, and it's giving us the opportunity to revisit quantum foundations. So this is something that I will talk about. I'll probably just give one lecture on it at the end of the course, but I want to talk about it now just in case some of you are interested in getting involved in the research, which I'll be running at while I'm here. Okay, so so in terms of fundamentals, so this is really the way I'm doing this lecture. I'm simply going to ask questions. So, and these will be the sorts of questions, if you don't know the answer to them now, you will by the end of the course. So when is surface tension important? Who cares about it? Particular, how can we understand the dynamics of all of these things? Drops, bubbles, soap films, fluid sheets, impacts, and waves. Okay, so on a day like today, you can ask yourself, how different would the world be if raindrops were that big instead of this big? Right? And what determines their size? Well, as we'll see, it's surface tension. Right? So we know now that if we throw a huge bucket of water off the roof, it will go through some sort of shape distortion like this. It goes into a parachute, and that parachute then breaks up, and ultimately you get things which are about a millimeter in size. And so we'll be able to rationalize the size of raindrops and see that it's determined, in fact, by surface tension. Okay? And when rain hits a puddle, we get quite elaborate flow structures, and we'd like to be able to rationalize these. Okay, so we see in particular, we see this crown, this incident raindrop, you see this crown, this splash crown, and this ruptures, gives rise to micro droplets, and then following this you have this jet coming up, that again pinches off. So we want to try and rationalize the size of the final droplets, and this will depend on the energy of the impact as well as, of course, the surface tension. And this is sort of general question. It's called fluid atomization. So you have a large volume of fluid which is being broken up. It will typically break up into sheets, filaments, and ultimately drops. And one wants to be able to trace the steps as you go through. So this is important in fuel injectors, various industrial problems, generation of aerosols through sprays, same sort of mechanics. And here's some slightly more aesthetically appealing shots. This is an artist who's taking some beautiful shots of interfacial flows. One of the reasons I like this subject is that it has a very strong aesthetic appeal. And this is basically a single shot from the last experiment where you have a raindrop coming down, and you can actually see from the color, you can have the raindrop, which is one color, and the bath a different color, and you can see the extent to which mixing occurs. So the fluid ejected after the impact is going to be some combination of the bath fluid and the incident drop fluid. Okay, so here's a really patchy experiment, but you see the same sort of thing. And this is, people seem to keep writing on this experiment. This is Harold Edgerton, who's a professor at MIT, and he was famous for taking these he basically developed strobe photography and high-speed videography. And this is an early picture he took. This is called the Edgerton crown, after him, and people seem to keep studying this problem, although it seems to me that it's been solved for a long time.
So yeah? How fast is this so that you can see that this spoon?
So you certainly don't need a very high-speed camera, certainly 500 frames per second. I think that's maybe slowed down by a factor of 10 or something. Yeah, I'd say 10. And that looks like milk. Yeah, it looks like dyed milk. But this is a raindrop hitting it. It's a thin layer of milk. Right? And you get this structure. But again, so you'll be able to, by the end of the course, you'll be able to say rationalize that spacing and the size of the drops. Okay, so these are, again, the same guy, Martin Waugh, who has these very artistic shots of similar things. And we can rationalize what's going on here. He's slightly cheating, actually, because he releases one drop and you get this this so-called Worthington jet, this jet that shoots up, and then he drops another. So then you have a drop impacting on a jet. So you get this umbrella type structure. Okay, and this is one of our experiments. So this is a dense hydrophobic particle. So it's water repellent. And so despite the fact that it's heavy relative to water, it bounces because the energetic cost of submergence is so high. Right? So it's basically the surface chemistry and the surface roughness contribute to its water repellency, so it doesn't want to be underwater despite the fact that it's actually heavier than water. So it will remain suspended on the interface despite the fact that it's heavier than both the air and the water. Okay, and so other questions. So if we put a fluid drop on a substrate, how can we rationalize the shape that it takes? Okay, and this is going to depend on both the chemistry and the surface. So the surface tension will depend on the. So there's basically we'll start thinking of surface tension as being an energy per unit area, which is present both at an interface like that and an interface like this, and an interface like that, even solid gas interfaces. And so those three all contribute to the shape of the drop. Okay, so if we have now a soap film, you've all blown bubbles. If you break a soap film, how quickly does the sheet retract? And when is the front stable? So if we have a more complex geometry now, we have start off with a spherical bubble. We pop at the top. This thing retracts. And you can not only predict so there are in this geometry you also have shape changes, so you can try and rationalize these. So if anything dealing with sheets one can describe mathematically. So today I'm just showing you pictures and videos, and we'll develop the mathematics in subsequent lectures. Okay, so here we have a soap film with a rod, and so we have a tensile force per unit length is the surface tension. When we pop one side, there's a unbalanced force, so this then gets pulled in that direction, and we can rationalize the speed of the rod. Okay, and so now these are nice. This is a nice subject for mathematical optimization. So here you can ask what is. Basically, you think of surface tension as a surface tension per unit area. So systems dominated by surface tension always want to minimize the surface area, right? And so we can then rationalize the shape taken by a fluid film suspended between two rings and find that it's a catenoid. Okay, so if we start off with a fluid thread, a cylindrical fluid thread, it will pinch off into droplets in an attempt to minimize the surface energy of the system. And on the basis of this, one can rationalize the most unstable wavelength, okay, which is we'll see is always about 10 times the initial diameter of the thread. Now, if we have, so this is what happens. We know when we release a fluid jet into the atmosphere and watch it pinch off. If we have now a jet impinging on a bath, so this is if you just turn on your tap and hold a glass of water, you'll see this. You'll see that there are waves, standing waves on the surface of the jet. And these, you can calculate this wavelength because it turns out that these are the waves that are traveling up at the same speed that the jet is traveling down. So you simply find the wave whose wave speed is equal to the incident jet speed. And those are the waves that you'll see on the base of the jet. Now, on this guy, now we have the same experiment, except we put in soap on the surface of our glass now, and soap reduces the surface tension, and so relative to water. So that means you have high surface tension here relative to here. So there's a gradient in surface tension which acts in this direction. It actually acts to rigidify the jet. Okay, so if you blow in some dust onto the system, so for example, chalk powder will simply sit on the surface of the jet. Okay, so because you have this surface tension gradient, which is a surface stress, that balances the viscous stress associated with the pipe flow. So this is basically a rigid pipe at the base of the jet, and so this jet enters the reservoir as if through a rigid pipe. And then above, where all this, where the soap is collected, you have the same business as we had here. Okay, so surface tension gradients, so-called Marangoni flows, will also be highlighted in the course.
Killing the high frequency?
Yeah, the soap is actually acting as a surfactant, but you can use the dust just as a tracer. So, because when you blow it on the surface, it just sits there, because the surface is rigid, right? Yeah, even without the dust, yeah. Okay. Okay, and so it's another sort of canonical problem in fluid dynamics, the hydraulic jump. So you have a jet of fluid hitting a puddle, and what happens is the fluid is ejected out radially, and it goes out in a thin layer. So we basically have a bath with some depth of a few millimeters. You have this thin layer now, which then jumps suddenly in height at a critical radius. And so we can ask, what is setting this radius? And surface tension is important when the jumps get small. And surface tension is important for the resulting instability. So in a certain parameter regime, despite the fact that you have an axisymmetric source, that is to say a circular jet striking a flat puddle, you get these instabilities. So you get these polygons emerging. And this is still actually not well understood, this problem. No, it's steady. So it's steady. So there are two sets of solutions. You can have steady ones, steady polygons, or you can have rotating polygons. Okay, and you can have polygons, or you can have other things. And you can see actually there's actually like a double jump here. You can see two steps. And so it's a very rich problem. And certainly surface tension is important. Okay, so actually, Thomas Bohr discovered those polygons. And got me interested. I said, well, I wonder if we can get the same thing in free sheets. So here we have a jet of fluid coming down and being squeezed out of this circular annulus. And so we have this radially expanding sheet. And as we'll see, so what is its radius? The radius is set by the balance between the inertial force, which is radially outwards, and the surface tension force, which is inwards. If you balance those two forces, you calculate the radius, okay, of the sheet. But again, in a certain regime, these sheets go unstable and you get polygons emerging. So how do we rationalize this? If it sags under the influence of gravity, so basically in these previous shots the film was flat because basically the speed was so high that it gets to the edge before gravity plays a significant role. You can also, if you have lower speeds, then gravity will have an effect and will tend to dip down. But again, you see these the polygonal instability. And there's this funny regime now, which I never understood this one. This one always confused me because so now we're actually shooting the thing. We can control the takeoff angle with this lip on the impactor. So this one's actually going up slightly. But you see it's going up, and then it's suddenly turning, right? Which is very strange because both inertia and surface tension want things to be slowly moving. Surface tension doesn't like sharp turns, and neither does inertia. But nevertheless, you're getting these corners in these free sheets, which is very strange. And I think a recent paper now has convinced me of what's happening here. But, question?
Yeah, is this like a steady profile?
Yeah, so this is steady, yeah.
I mean, you don't have to strobe it to see this?
No, this is absolutely what you see with the naked eye. You turn it on in the lab and you see this, yeah. Okay, and so again, in the regime where gravity is important, the thing you'd expect fluid striking an impactor to follow a parabolic trajectory, and it does, but then because of surface tension, there's this additional tension which causes the bell to close. Okay, and so then you basically generate then a bubble, but of course it's a dynamic bubble because the fluid's going around like this, and once again, if you change the viscosity, then you again break the symmetry and you get this sort of polyhedral shape.
Okay? It's like a water bubble in the air instead of...
Right? Yeah. Okay, and so this was kind of an interesting story. So this grew out of the sheets because we saw in a certain regime here, these coming out of the corners of these sheets were these things which looked like fluid chains, and so you can generate these from the collision of two jets. So how do we rationalize the shapes of these so-called chains? So there's actually a thin sheet there, but then we have the rim on the sides. This is a blow-up. So these are the two impacting jets giving rise to a sheet in the plane. So the jets come like this, and then you have a sheet in the plane perpendicular, and these develop rims which then collide, giving rise to a sheet in the plane perpendicular, and so on. So we were interested in these, and we were studying these fluid chains. This is something you can see if you pour from a lipped jug water or wine. And then if you crank up the flow speed, so here we have two jets colliding, and this fluid chain becomes unstable. And if you strobe it at the right frequency, so this is what you see with the naked eye, but when you strobe it, you see this very regular structure emerging. And so what's happening is you're getting this pinch off of the rim, just like when you have pinch off of a fluid jet. And because this is moving along a curved surface, the bulbous regions are flung outwards, and you get this fishbone structure.
Inside, John, what is the speed profile, say, in this very thin inside region?
It's basically just going like this. It's moving in a straight line.
Is it moving slower than the outside part, or not?
About the same. So yeah, you basically just have some angular profile, but the velocity within the sheet is actually uniform. But then here,
I would guess it's faster there, but I'm not sure if I'm guessing right.
Yeah, it's good. I think it should be around the same. I think there's basically no relative motion between here and here, apart from that associated with the instability of the rim, and again the fling outwards. Yeah, so to leading order, this speed is the same as that speed. Yeah, yeah.
That's exactly the same picture?
These are exactly the same. This is what you see with the naked eye, and this you get when you strobe it. So you basically, I think it's 300 hertz or something. And so this, when you have a strobe on it and you strobe it at the right frequency, this is what you see. So it's basically frozen in...
Basically that thing is happening all the time, but I'm wondering what happens in between those.
Yeah, so this is basically just sweeping downwards, right? So this is evolving from that into that, right? And so this is why you don't see that. All you see is these stripe. That stripe there corresponds to this stripe here, and this stripe here to this one here. Okay? So you're simply right, and so similarly, so these are some more of the elaborate structures, but much of interfacial flows can be understood from the single instability of a fluid jet pinching off, which we'll go through in detail. But that's giving rise to the structure here. Oops. So this can be thought of as instability of this rim, right? And these then get flung out by the centripetal force, giving rise to these, and these then pinch off in a similar fashion, right? So these are then pinching off again by Rayleigh plateau, and so again this filament is pinching off, same instability. And so you can always rationalize the wavelengths of instability of a filament with this single instability. Okay, and so now if we have a fluid jet which is rotating, rotation wants to fling things outwards. We have this. We know we have this tendency to minimize surface area, and it's that which causes the pinch off. But we get more elaborate structures when things are rotating. Particularly, we see this sort of staircase structure, and the fluid jet. Now, so we saw that bells can close owing to the influence of surface tension, but when things are rotating, you get multiple closing events, so the thing doesn't close completely. You get waves, and so we can rationalize this wavelength and the fact that it never closes. Okay, so here's an example of a non-coalescence problem. So here we have a fluid jet. It's a silicon jet hitting a bath, and it's basically going in and out and not coalescing. The reason is you simply maintain an air layer between the jet and the underlying bath. Okay? And this is these non-coalescence events I've been interested in for a long time. This is sort of what generated my interest in this quantum problem, which we'll talk about. Yeah.
In your previous slide,
Uh-huh.
you have like a little spiral thing. Is that the fluid or is it material? Is it solid?
Where, here?
On the second one. There's like a little spiral.
This
in
one,
the
the
middle.
blue one. Yeah, that's just like the.
This?
That's like this. No, the spiral, like a hose.
Oh, yeah.
It looks like something solid. Is it just a fluid? Or?
No, it's just a fluid. Yeah. So that's the accumulation of the.
Fishbone one, right? It's just like the
Yeah,
outer part.
yeah. You see the rim. Yeah, you see the rim. It's sort of got it's got like a helix. It's got a helical rim, right? So the sheet is actually like a surface of a. Yeah. Okay, and so these are nice problems. Here again, the pinch off we can understand, but the odd business is this non-coalescence. Okay, and so this I looked at earlier, and I've come back to motivated by this quantum problem, which I'll discuss at the end. But here we have a fluid jet, which is basically pinching off. You can see that in certain regime, the drops will bounce. In others, they will merge. And so it's a matter of maintaining the air layer between the drop and the bath. Okay, and so here's a nice, this for me is the most beautiful experiment because it's very simple, it's very rich mathematically, and the physics is subtle too. So this happens, and plus this happens every single day. Right now it's happening in Rio 1 billion times a minute. So we
don't see it. Right?
Yeah, exactly, you don't see it, it's just too fast, right? So this is slowed down by a factor of 50. If you look very carefully with your naked eye, sometimes when you put milk in your coffee, you can see, you go, what is it? You can see it rolling and then decreasing in size. And each time it's decreasing in size, it's happening discretely through this. This is called the coalescence cascade. So basically it dumps, its radius decreases by a factor of 2, and it jumps up in there. So what would you expect? You put a drop of water on water, you expect it to maybe take some time for the air layer to drain, then it'll just go like this. Yeah. But in fact, you see this very elaborate dynamics. I've long been interested in this problem, and finally my first graduate student did this. It actually required numerics, which is, for me, is a rarity. Normally, I feel that I can solve problems without doing any numerics. Yeah, that's right. But he took it to the next step and did the numerics required. But it turns out what happens is you have, when it merges, you get waves generated at the point of contact, and these waves sweep upwards, and there's an associated momentum transfer, which gives rise to a force which drives the drop upwards. Okay?
It's the wave that makes the drop jump then.
That's right. So these are shot. So this is I did a TV show with Discovery Channel because I wanted to get this shot with the nicest cameras, and so I kept an eye on the TV show, and it went for I think about a year or so, and then it was discontinued. So I bought their camera. So I now have this camera in our lab. That's a nice camera. Okay, so here's a similar problem. Now what happens if the surface tension of the bath and the drop are different? Those are both water-on-water experiments. Here we have water going onto alcohol. Alcohol has lower surface tension than water. So you expect a merger, but then you see, again, because the surface tension is higher, it drags more fluid upwards when it merges. Okay? So just like in that jet experiment, you have a surface tension gradient, and this gives rise to anomalous forces and changes the dynamics. Okay, so this is non-coalescence. Here we're vibrating the bath. So this is sort of the starting point for the quantum business. But so the question is, why doesn't it coalesce? As I've already told you, it's because you have this air layer between the drop and the bath, and provided the contact time is short enough, then the thing will bounce indefinitely. Okay, so now you can also have impact on soap film. So we have a drop of soapy water hitting a soap film, and as you expect, sometimes it will break through, sometimes it won't. If it's a very high speed, the kinetic energy of the system is greatly exceeds the surface energy, so the thing will pass through. If not, the soap film behaves like a trampoline, and you can describe the dynamics exactly. Because the surface area is changing as a function of the position of the drop, the force on the drop is changing. Okay, and so simple problem, but rich dynamics. So you can either pass through, it can, and it's actually, I should mention.
They're the one coalesced in the air, right?
Yeah, so you can get partial coalescence here as well. So this one actually passes through, but a drop gets flung upwards, right? And then it can also get stuck in the film. Okay. And it's kind of interesting. I should mention this, but why? So notice in this one, the drop actually goes through, and the film doesn't break, right? So basically, what happens is the drop comes down, it enters into the film, so it becomes part of the film, and then it falls out of the bottom of the film, but it doesn't break the film. And why doesn't it break the film? It doesn't break the film because the film is soapy. If it was pure water, the film would break, but it's not pure water. Soap basically makes the interface behave as if it's elastic. Okay, which is why these things behave like trampolines. Okay, and so again here, the drop enters into the film and then either falls out the bottom or can be flung out of the top. Okay, and so this is something that perhaps you considered at Réveillon this year. What are the wine tears? So this is actually the first example of a problem. This is actually mentioned in the Bible. But it's the first problem in which surface tension, the dynamics associated with surface tension is dominant. So it turns out that surface tension is a function of alcohol concentration. And so in your wine glass, if you take a sip or you swirl the glass, and you get a thin film here, and surface tension decreases as the alcohol concentration increases. Alcohol, we know, is volatile, so it evaporates from everywhere along the free surface, right? So basically, alcohol is being sucked out of the wine everywhere, but in the thin film, the surface area to volume ratio is higher, right? And so it loses alcohol fastest in the thin film. Okay, so you have less alcohol in the thin film relative to the bulk, which means that the surface tension is higher. So there's a surface tension gradient which pulls fluid upwards. So you basically have this surface stress which drags fluid up into the thin film, and it accumulates at the top of the thin film in this band which grows until becoming so large as to go unstable and release the tears of wine. So these are constantly being replenished. They'll sit there driven by this, basically the chemical potential energy generated by the evaporation, and this goes until basically the system runs out of gas, the gas being the alcohol. And there are all sorts of very peculiar flows which are generated by surface tension gradients. So here's one of them. So here you're just releasing a drop of heavy fluid into light fluid. This is what you expect. It'll simply pinch off and go. But here it starts the chemistry is a little bit different, and you get this very peculiar dynamics. This thing just keeps spitting out micro droplets, and this has to do with the chemistry of the situation. There's basically some chemical reaction going on the surface of the drop, which gives rise to this very rich dynamics. This is Bud Holmes's experiment. Okay, and then this problem here, the next problem I like. This is something that one of my senior colleagues, when I first arrived at MIT, he said, "I've got a problem for you." And so he showed me this experiment. So he put a drop of oil onto the surface of water, and it goes woof, 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 and it beats spontaneously. I go, "What is that?" And so he was torturing me with this problem for about 2 years. I really didn't. And he goes, I said, "What's going on?" He goes, "I don't know." And so that was the question. I had to try and figure it out. But what he didn't tell me was that there's a surface active material in the oil, okay, and it's a very complicated story actually. But I'll explain this at some stage during the course. But basically, the surface tension in the system is changing as a result of evaporation and various other things. But we did finally figure it out. But this is there's a German count at the end of the last.
Sorry, do you see this at naked eye now?
Yeah. This is real time. This is just this is real time. So it just goes boop 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 boop. But
It's oil and water.
Yeah, it's oil and water. But the oil has something in it, which changes the surface tension. And so there's a German count at the end of the last century who was interested in finding mechanical analogs for biological systems. So this was his biological clocks, which was he considered a model of the beating heart. Right? Okay. Good. That's a good time for a break. Okay, we're going to have a 5-minute break. So we're going to have 3-part lecture. So we can stop for a second.
Okay.
So that's part 3. Good. 45 minutes. We'll go faster to the next part.
Soccer skill, right? 45 minutes.
What's it for 3?